Okay, so let's unpack this. Imagine you've got this incredible stack of sources, articles, research notes, all focused on how our planet works, from the ground beneath us right up to the air above.
Yeah.
That's what we're diving into today. Our mission really is to cut through all the noise, pull out the absolute core insights from this material, and, well, get you well informed quickly.
And find some of those surprising connections along the way.
Exactly, those aha moments. The sources you've shared cover a massive range.
Mm.
We're talking Earth's basic systems, the resources we use every day, energy, climate stuff, plate tectonics.
And even how we as humans fit into the picture with population dynamics.
Right. So this deep dive is all about connecting those dots, showing how these seemingly separate ideas actually paint a much clearer picture of, how our planet works and our place in it all.
Makes sense.
So let's kick off with this fundamental idea that seems to run through everything, that all the geoscience fields are part of one massive interconnected web. The source is called Earth System Science, right? And they break Earth down into these 6 key spheres.
Yeah, thinking about Earth as a system is, well, it's really powerful. It helps you see those connections. The material points to these 6. The atmosphere, that's the air, the hydrosphere, all the water, the biosphere, life, the geosphere, the solid planet itself.
The lithosphere, that rigid outer part with the plates?
Exactly, the lithosphere. And then there's the anthroposphere, which is basically us, our cities, our infrastructure, everything humans have built.
And it's fascinating how, for each sphere, the sources actually pinpoint specific resources we draw from. Like, the atmosphere gives us wind for energy. Hydrosphere gives us fresh water, obviously vital. Biosphere, well, that's our food.
Yep, plants, animals.
Geosphere is where we get metals and minerals.
Yeah.
Lithosphere provides building materials, stone, sand.
And the anthroposphere, our own creation, is actually a source, too, for things like concrete and steel, the stuff we use for more infrastructure.
It's kind of a cycle in itself there.
It is. And how we categorize these resources is super important. The material draws a really clear line. Renewable versus non-renewable.
Okay, so what's the core difference according to the sources?
Well, it boils down to time, really. Renewables replenish naturally on a human timescale. Think solar, wind, even timber, if you manage it right. You can theoretically use them indefinitely.
Right, sustainable.
Non-renewables, though, they're finite. They exist in fixed amounts, and we use them way faster than they're formed. Coal, oil, uranium. They're not getting replaced anytime soon on our timescale.
And that difference isn't just academic, is it? It totally changes how we should approach using them.
Oh, absolutely. It dictates the strategy. Renewables lean toward sustainable use. How do we keep this going? Non-renewables demand careful management, thinking about depletion, and finding alternatives, because they will run out.
Plus the environmental side effects.
Exactly. Big ones, often. The sources really flag that trade-off. Renewables are cleaner, generally, but often intermittent sun doesn't always shine, wind doesn't always blow. Non-renewables are often super energy dense, reliable for now, but, polluting and ultimately unsustainable.
Okay, let's shift gears a bit and zoom in on energy itself. It's so central. The material gets right down to the basics of measuring it, starting with the fundamental unit, the joule.
That's the science standard, yeah, the base unit. But, as the sources point out, a joule can be tiny or huge depending on what you're measuring, so we often use specialized units.
Right, like the ones they mentioned.
Yeah, 2 good examples. The calorie, the one we see on food labels, that's actually a kilocalorie, technically, and it's equal to 4,184 joules. Quite a lot.
And then the other extreme, the electron volt, EV, for physics stuff.
Tiny. Used in particle physics, it's about 1.6 times 10 to the minus 19 joules. Shows the massive range of scales energy operates on.
It really does.
And then there's power, which is energy flow over time. That's measured in watts, WA.
Okay, so 1 watt is just 1 joule flowing every second.
Precisely. The light bulb example they use is perfect. A 60-watt bulb, it's using 60 joules of energy every single second it's on. Helps you picture power as a rate of use.
Got it. Okay, so let's connect energy back to a huge global resource. Oil. The material makes this really key point about oil prices. It's not just the cost of drilling, is it?
Not at all. Far from it. It's this complex dance of global supply and demand, heavily influenced by, well, everything: politics, financial markets, the overall health of the economy.
And this is where it gets super interesting. The sources used the 2008 financial crisis. Wow. They note oil prices crashed from over $140 a barrel down below $40.
Yeah, got a massive plunge.
And crucially, it wasn't because drilling got cheap or someone found a giant new oil field overnight.
No, the supply side didn't change that drastically. What happened was the global economy basically slammed on the brakes. Industries cut back, transportation slowed right down, manufacturing dipped,
So demand just evaporated.
pretty much plummeted worldwide. That price collapse was a direct reflection of how little oil the world was suddenly using. It just shows how sensitive that market is to these big economic shocks, way beyond just the physical supply.
Okay, let's move up from the ground to the air, the atmosphere, and this critical idea, the greenhouse effect. The sources start with the basics. What's actually in the air?
Right. Mostly nitrogen, about 78%. Then oxygen, around 21%. Argon makes up almost another percent, about 0.9%. And then you have all the trace gases in much smaller amounts.
And the key thing is how these main gases, nitrogen, oxygen, argon, interact with heat radiation, right? The long-wave stuff Earth emits.
Exactly. They basically don't. They're transparent to that outgoing infrared radiation. So they aren't greenhouse gases. They just let the heat pass through.
Okay, so greenhouse gases then are the ones that do interact with it. They absorb and re-emit that heat,
Well,
kind of like a blanket.
That's the core idea. The material defines GHGs as atmospheric gases that absorb and then re-radiate that infrared energy. This traps heat, warming the lower atmosphere and the surface. It's the greenhouse effect.
And why do some molecules do this?
It comes down to their shape, their molecular structure. Molecules with 3 or more atoms, like carbon dioxide, CO, methane, CH, water vapor, HO, or even ozone, are asymmetrical molecules. They can bend and vibrate in ways that let them absorb that specific infrared energy.
Unlike the main ones.
Right. Simple, symmetrical molecules like nitrogen and oxygen, or single atoms like argon, RO, they just don't have the right structure to vibrate in that heat-absorbing way.
And these GHGs, they're not all equal offenders, are they? Some pack a bigger punch or stick around longer.
Definitely not equal. That's a key point the sources make. They vary a lot in how strongly they warm things up per molecule. That's often measured by global warming potential, or GWP, usually compared to co-Euros over 100 years. And they also vary hugely in how long they last in the atmosphere, their lifetime.
Can you give some examples from the sources?
Sure. Co-Euro is a baseline, GWP of 1, but its lifetime is enormous, hundreds, even thousands of years. Methane, CH, has a GWP around 28 over 100 years, so it's much more potent short term, but it breaks down faster, lasting only about 12 years.
Okay.
Nitrous oxide, N-Euro, that's got a GWP around 310 and lasts over a century. And then you have some industrial gases like SFEO, sulfur hexafluoride. Its GWP is staggering, around 25,200, and it lasts for thousands of years. Tiny amounts have a huge impact.
What about water vapor? It often comes up.
It does. Water vapor, H2O, is actually the most abundant greenhouse gas. And yeah, it has a strong warming effect. But its lifetime in the atmosphere is super short, just days. So the sources explain, it mainly acts as a feedback.
A feedback? How so?
As a planet warms from other long-lived GHGs like CoYos, the warmer air can hold more moisture. That extra water vapor then traps more heat, amplifying the initial warming. So it ramps up the effect, but it's not the primary thing driving the long-term trend.
I see. So stepping back, this natural greenhouse effect, it's essential for life, right? Keeps us from being an ice ball.
Oh, absolutely essential. The mechanism is pretty clear in the sources. Sun sends shortwave energy, visible light mostly. It passes through the atmosphere, warms the Earth's surface. Earth then radiates that energy back out as the long-wave infrared heat. The GHGs in the atmosphere catch some of that outgoing heat, absorb it, and re-radiate it in all directions, including back down. That trapping process keeps the planet much warmer than it would be otherwise, habitable.
And the key players identified again are water vapor, co-Euro, methane, nitrous oxide, ozone, and those industrial ones.
Those are the main ones, yes. And the overall strength of this warming effect, throughout Earth's history has changed depending on how much of these gases were in the air.
And there's a direct link between those concentrations and Earth's temperature over time.
A very strong link. The material points to evidence from ice cores, geological records. Choosing in co-Euro, methane, nitrous oxide levels correlate really well with past ice ages and warm periods.
Wow.
And here's a striking fact from the sources about the recent changes. Since just 1990, the warming influence, what scientists call radiative forcing from just the long-lived greenhouse gases, has increased by over 50%.
50% since 1990.
Over 50%. That's a huge boost to the warming effect in just a few decades, and it's what's driving the current warming trend.
There's also this really neat detail in the sources about atmospheric corros, how it actually goes up and down predictably over just 1 year, like the planet breathing.
Yeah, it's exactly like that. The
Yeah.
Keeling Curve shows it beautifully. Corridor levels peak in the northern hemisphere's early spring, then they drop, hitting a low point in late summer or early fall.
Okay, but why does it do that? What causes that annual cycle?
It's mostly driven by plants, especially the vast forests and vegetation in the northern hemisphere,
Hmm.
just because there's more land mass there. In spring and summer, plants go into overdrive with photosynthesis, sucking huge amounts of co-rose out of the air to grow.
So levels drop.
Levels drop globally. Then, in the fall and winter, photosynthesis slows way down, plants shed leaves, things decompose, and respiration continues. All that releases co-rose back into the atmosphere, so the levels rise again.
So that up and down is totally natural.
Completely natural seasonal cycle.
Hmm.
But, and this is the crucial point the sources make, that natural breathing is happening on top of a much larger, relentless upward trend caused by human activities.
Mostly burning fossil fuels.
Primarily burning fossil fuels, plus land use changes, like deforestation. The sources note we're now over 420 parts per million of co-Euros. That's up about 151% from pre-industrial times. So you have the natural wiggle, but it's riding this steep escalator upwards.
Okay, powerful image. Let's switch gears and dive down to the solid Earth. Igneous rocks. The material explains how they form.
Yeah, igneous means from fire, essentially. They form when molten rock magma below ground or lava on the surface cools down and solidifies, crystallizes.
And there are two main types based on where they cool.
Right. If magma cools slowly, deep underground, it forms coarse-grained rocks called intrusive or plutonic rocks. Granite is a classic example. Lots of time for crystals to grow big.
Okay.
If lava erupts onto the surface, it cools very quickly. That forms fine-grained or even glassy rocks called extrusive or volcanic rocks. Basalt, like you see in Hawaii, or obsidian, which is volcanic glass.
And we get some really valuable stuff from these igneous rocks, don't we? The sources list a few.
We do. Gold, for instance, is often found in hydrothermal veins that are related to igneous intrusions, crucial for electronics, jewelry.
Right.
Graphite used in pencils, lubricants, steelmaking, can form in specific igneous settings called pegmatites. And uranium, the fuel for nuclear energy, is often concentrated in certain types of granites and related igneous rocks.
So moving from the rocks themselves to how the Earth's crust moves plate tectonics, what actually makes these giant plates shift around?
It's driven by immense forces originating from Earth's hot interior, and also involves gravity acting on the plates themselves. It's a combination of things.
And the main driving forces mentioned are slab pull, ridge push, and mantle drag.
Those are the big three, yeah. Slab pull is generally thought to be the strongest. That's where a cold, dense oceanic plate sinks back into the mantle at a subduction zone. Its own weight literally pulls the rest of the plate along behind it.
Like an anchor sinking.
Kind of, yeah. Then there's ridge push. At mid-ocean ridges, new, hot, buoyant crust is formed. Because the ridge is elevated, gravity causes this new crust to sort of slide downhill, pushing the plate away from the ridge.
Okay. And mantle drag.
That's the friction between the bottom of the plate and the slowly flowing, convecting mantle rock beneath it. Depending on the flow direction, it can either help pull the plate along or resist its motion.
So let's picture the specific scenario from the sources. A thin, dense oceanic plate crashes into a thicker, lighter continental plate. What happens?
Subduction. That's the key process. Because the oceanic plate is denser, it dives or subducts underneath the lighter continental plate.
And that creates some dramatic features.
Oh yeah. These are incredibly active zones. You get a deep ocean trench right where the plate starts bending down. You get powerful earthquakes happening at various depths along that sinking slab that's called the Wadati-Benioff zone.
And volcanoes.
Definitely volcanoes. As the oceanic plate sinks, it heats up and releases water. This water lowers the melting point of the mantle rock above it, creating magma. That magma rises to the surface and erupts, forming a chain of volcanoes on the overriding continental plate. Think of the Andes or the Cascades in the Pacific Northwest.
Wow. Plus mountains and altered rocks.
Right. The collision also causes buckling and folding, building mountains. Sediment scraped off the downgoing plate can pile up, and the intense heat and pressure metamorphose existing rocks, changing them into new types. Subduction zones are really geologic factories.
Okay, let's bring this whole conversation back to us, humanity, and our impact, starting with just our numbers. The sources say global population is over 8 billion now.
That's right, over 8 billion. And the 2020 growth rate cited was around 1.1% per year.
Which, if that rate just kept going.
Hypothetically, yeah, if it stayed constant, the population would double in about 63 years. You'd be looking at over 15 billion people by 2100. But, and it's a big but, the sources are very clear. That's not what's expected. Global growth rates are slowing down.
Still, the material asks that crucial question: is sustained high growth, even if it's slowing, truly sustainable? And the answer seems pretty clear.
The answer from the sources is a definite no. Continued high growth puts immense strain on resources, water, food, energy. It worsens climate change impacts, increases pressure on ecosystems. Real sustainability, they argue, requires both slowing population growth and fundamentally shifting how we consume, moving to renewables, developing more equitably.
And the UN projections cited suggest the population might peak somewhere around 10.4 billion, maybe around the year 2086, and then potentially level off or even begin a slow decline. But that assumes fertility rates continued to fall in many parts of the world, which is the current trend but not guaranteed. So how exactly does adding more people increase resource consumption? The sources break it down into two main pathways.
Right. First, it's pretty direct. Increased demand for energy and industrial products. More people need more electricity for homes, more fuel for transport, more manufactured goods. This drives up demand, especially for energy, and a lot of that still comes from fossil fuels.
And the U.S. example really highlights that leverage effect.
It does. Around 4% of the world's population using something like 17% of the global energy. When you combine population growth with economic development and high consumption levels, the impact really scales up.
Okay, and the second major pathway is food and agriculture.
Exactly. Feeding billions more people requires more land for crops, which often means clearing forests, releasing carbon dioxide. It also typically means raising more livestock.
And livestock have their own climate impact.
Big time. The sources point out livestock farming is a major source of methane, that powerful greenhouse gas we talked about. So both expanding cropland and raising more animals puts pressure on land, water, biodiversity, and contributes directly to climate change.
To help visualize these population differences, the sources talk about population pyramids. What are those telling us?
A population pyramid is just a graph, really. It shows the distribution of a population by age group and sex, but its shape tells you a ton about what's going on. Birth rates, death rates, how long people are living.
And the examples they use, Uganda and Norway, are like night and day.
Totally different shapes, tell totally different stories. Uganda's pyramid has that classic wide base, tapering really quickly to a narrow top. That shape shouts. High birth rates, lots of babies and young kids, but also high death rates, especially among children, so fewer people survive to old age. It's typical of a country maybe in stage 2 of the demographic transition, rapid growth.
And Norway, developed country.
Norway's pyramid is much more like a column, or maybe a bowling pin, as the sources say. Relatively narrow base, low birth rates. And it stays wide, much higher up, low death rates, high life expectancy. Most people born survive to old age. That's typical of stage 4 slow or zero growth, maybe even decline. The shape itself shows you survival patterns.
And then there's that great comparison, the tale of teeming cities, Singapore versus Lagos, highlighting 3 specific differences.
Yeah, it really brings it down to the city level.
Yeah.
First, fertility rates. Singapore's is incredibly low, well below replacement level, like 0.97 children per woman. Lagos is high, so pyramids look totally different at the base.
Okay.
Second, age structure. Singapore is aging rapidly, median age over 40, lots of older people. Lagos is super youthful, median age under 20, partly due to migration. Third, migration. Singapore relies on international migrants to fill jobs and support its aging population. Lagos explodes largely due to young people moving in from rural areas looking for work.
And life expectancy reflects those differences too.
Hugely. Singapore's is very high, around 83 years. Lagos is much lower, maybe 55 to 60 years, reflecting challenges with healthcare, sanitation, etc., in rapid urban growth. So yeah, birth rates, migration, health, they all sculpt those city pyramids.
Okay, this all leads perfectly into the final big concept, carrying capacity. What does that actually mean for Earth?
The definition of the sources is pretty clear. It's the maximum population size that a particular environment can sustain indefinitely without degrading the resource base and the ecosystem itself.
So if a population is way below that limit,
then resources are usually plentiful, conditions are good, and the population tends to grow, often rapidly until it starts to approach that limit, where resources become scarcer or waste builds up.
the sources mention estimates for Earth's carrying capacity, but they seem to vary quite a bit.
They do. The numbers cited often fall in a range like, say, 8 billion to maybe 16 billion people.
Yeah.
But, and this is the really critical point, they stress it's not a fixed number carved in stone.
It depends on us.
It depends hugely on how we live. What are our consumption levels? What technology are we using? How equitably are resources distributed? If everyone consumed like the average North American, the carrying capacity would be much lower. If we adopt sustainable practices and share resources fairly, it could potentially be higher.
So it's not static. We can actually influence it, for better or worse.
Exactly. Our actions can decrease it, things like overexploiting resources, pollution, climate change, destroying habitats, losing biodiversity. All those things degrade the environment's ability to support us.
But we could also potentially increase it.
Potentially, yes, through things like developing sustainable agriculture, shifting decisively to renewable energy, serious conservation efforts, reducing waste, and maybe technological innovations that let us use resources much more efficiently or clean up pollution. The point is, carrying capacity is dynamic, and it reflects our choices about technology, behavior, and environmental stewardship.
Wow. Okay. We have covered a lot of ground here, really digging into the material you provided. It's incredible how interconnected everything is.
Yeah.
From Earth's basic systems and resources to the physics of energy, the atmosphere's balance, the geology moving beneath us, and then layering on human population and our choices. Understanding these fundamentals really gives you a different perspective, doesn't it? A powerful lens for viewing the world.
It really does bridge that gap between the physical planet and the human story unfolding on it. And maybe, as a final thought, looping back to those last points, if the projections suggest a peak population around 10.4 billion later this century, and Earth's carrying capacity isn't fixed but depends so much on our actions, well, it poses a pretty profound question for all of us to think about, doesn't it? What responsibility does that place on us collectively, individually, to actively shape a sustainable future, to manage resources wisely, and essentially influence that carrying capacity through the choices we make right now?